Design specifications for a 3 kg drone. We are designing a 3 kg quadcopter following a proven 2:1 thrust to weight ratio. But notice how the application have evolved. We are now targeting professional aerial photography, surveying and mapping operations and light cargo delivery systems. This weight class represents a significant capability jump. At 3 kg, we can carry professional cameras, LiDAR sensors or meaningful cargo payloads. The drone becomes a serious commercial tool rather than an enthusiast platform. However, with this capability comes responsibility. A 3 kg drone falling from 100 meters carries substantial kinetic energy, approximately 3000 joules. This is why our engineering approach must be even more rigorous, our safety margins more conservative, and our component selections more carefully considerate. Now we will see what are the exact calculations for a particular drone designing considering the drone weight as 3 kg. So here we go. First, we will see what is the required thrust calculation. Let's begin a systematic calculation process now, noting how the physics scales with increased mass. Our total drone weight is 3 kilograms. So using Newton's second law, force required to lift is equal to mass into gravity, that is mg. So here mass of the drone is 3 kg and gravity we would be considering as 9.81. So we get the force required to lift as 29.43 newtons. With R2:1 thrust to weight ratio, for optimal performance, the total thrust required should be twice the force required to lift, that is 2 into 29.43 newton, that is 58.86 newtons, which we will round up to approximately 60 newtons. For our quadcopter configurations, the thrust per motor will be 60 newtons divided by 4, that is equal to 50 newtons per motor. Converting to gram force for component specifications, 50 newtons is equal to 15 newtons divided by 9.81 into 1000 grams. So that is equal to 1530 grams of thrust per motor. Compare this to a 1 kg drone, which required 510 grams per motor. We have tripled the weight, so we have tripled the thrust requirement also. The relationship is perfectly linear. This is fundamental physics. Thrust scales directly with weight for any given thrust to weight ratio. Each motor must produce 1530 grams of thrust at maximum throttle. This drives all subsequent component selection. Then next is the motor selection. With 1530 grams thrust requirement per motor, we enter a completely different motor category compared to our 1 kg design. We now target brushless motor in the range of 700 to 900 kilowatts range, significantly lower than the 2300 to 2600 kilowatt we use for the 1 kg drone. Why this dramatic change? Lower kV motors produce more torque at lower RPM, that is rotational per minute, allowing them to efficiently turn the larger propellers required for this thrust level. Notice our efficiency factor has decreased to 7 grams per watt compared to 8 grams per watt for the smaller drone. This isn't a mistake. Larger motors generally have slightly lower efficiency due to increased electromagnetic losses and mechanical complexity. This is a fundamental scaling principle in electric motor design. The power calculation per motor, that is the power required, would be 1530 grams divided by 7 grams per watt. So that is equal to 218.6 watts per motor. This is over 3 times the power of a 1 kg drone. The power requirement scale more than linearly with size due to decreased efficiency. Current calculation become more complex. We are now using a 6S LiPo battery providing 22.2 volts nominal. Higher voltage is essential for efficient power delivery at these power levels. Using Ohm's law, maximum thrust current is equal to 218.6 watts divided by 22.2 volts. That is equal to 9.85 amperes per motor. The cruise current at 80% throttle is equal to 9.85 into 0.8, that is equal to 7.88 amperes per motor peak current with 1.5 into safety factor, that is equal to 9.85 ampere into 1.5, that is equal to 14.78 amperes per motor. Notice how current requirements haven't scaled as dramatically as power requirements. This is the advantage of higher voltage systems. Higher voltage means lower current for the same power, reducing resistivity losses and heat generation. So we have completed the motor selection now. Now we will go to the next selection of components, that is the ESC selection, that is the electronic speed controllers. ESC selections becomes more crucial as the current level increases for 3 kg torque as compared to 1 kg. Heat generation increases with the square of current, so thermal management becomes paramount. Our peak current per motor is 14.78 amperes with a standard 38% safety margin. Required ESC rating is 14.78 ampere into 1.3, that is equal to 19.21 amperes minimum. Theoretically 20 ampere ESCs would suffice, but I strongly recommend 25 to 40 ampere ESCs for several engineering reasons. First, thermal heat room becomes more critical at these power levels. ESCs generate heat proportional to I square R losses. As current doubles, heat generation quadruples. Oversized ESCs run cooler and last longer. The second reason is the professional application demand reliability. ESC failure at 3 kg drone weight possesses significant safety risk and potential property damage. The cost difference between 20 ampere and 30 ampere is minimal compared to crash replacement cost. Next is the future flexibility. A 3 kg platform might later carry heavier payloads or use different propellers requiring higher current. Oversized ESCs provide upgraded headroom. And the last would be the professional grade ESCs in the 25 to 40 ampere range often include advanced features like telemetry, thermal protection and better EMI shielding. Features essential for professional application. After this, we have the fourth component, that is the battery calculations. Battery sizing also becomes more complex as we balance increased power demands with weight constraints and professional flight time requirements. Our flight time target is 20 minutes, that is 1200 seconds, longer than the 1 kg drone because professional applications require meaningful operational duration. So the current draw calculation would be per motor at cruise is equal to 7.88 ampere. So total for 4 motors will be 31.52 amperes. For 1200 seconds it would be 31.52 into 1200, that is equal to 37,824 ampere seconds. Converting 37,8200 divided by 360, that 360 is equal to 10.51 ampere hours, that is equal to 10,510 milliampere hours. With 80% discharge depth for battery longevity, required capacity is equal to 10,510 mAh divided by 0.8 is equal to 13,130 mAh. However, there is a critical decision point here. My slide shows both 6S, that is 22.2 volt for motor calculation, and 4S, that is 14.8 volt for battery selection. Let me explain this apparent discrepancy. For professional application, 4S batteries are often preferred despite higher current requirements because 4S batteries are more readily available in high capacities. 4S systems have proven reliability in commercial applications. 4S batteries are less expensive and easier to transport, and 4S systems have better spare parts availability. Using 4S, that is 14.8 volt instead of 6S, that is 22.2 volts, higher current draw. Power per motor is equal to 218.6 watts. Current per motor is equal to 218.6 watts divided by 14.8 volt, that is equal to 14.77 ampere. So the total current becomes 4 into 14.77 ampere, that is equal to 59.08 amperes. This requires large capacity, approximately 14,500 mAh for 20-minute flight time. Weight budget remains 40% of the total weight, that is 1,200 grams maximum. Practical selection would be 10,000 mAh 4S battery, accepting slightly reduced flight time for better system practicality. The next would be the propeller selection. So propeller selection changes dramatically as we scale up to 3 kg systems. We are now in the realm of Large efficient propellers that operate at lower RPM. For 700 to 900 kilowatt motors on 4S battery, optimal propeller size is 15" in diameter with 4 to 5" of pitch. This is a massive change from 6 to 8" propellers that we used on the 1 kg drone. So why such large propellers for 3 kg drones? There are several engineering principles applied for the same. The first is the momentum theory. Larger propellers move more air at lower velocity, which is more efficient. The power required to generate thrust is proportional to the velocity of air moved. Slower air requires less power. The second is tip speed limitations. Propeller tips approach sonic speeds at high RPM, creating noise and inefficiency. Larger propellers at lower RPM stay well below these limits. The third is Reynolds number effect. Larger propellers operate at higher Reynolds numbers, improving aerodynamic efficiency. The pitch range of 4 to 5.5" provides flexibility for different applications. The 4" pitch has the maximum efficiency for hovering applications like photography. On the other hand, the 5.5" pitch has higher forward speeds for mapping and survey work. The material selection becomes critical at this size. Carbon fiber propellers are almost mandatory due to the centrifugal forces involved. A 15" propeller spinning at 4000 RPM experiences tremendous stress, and the plastic propellers would flex excessively, reducing efficiency and potential failure. So, the sixth component would be our frame considerations. Frame design principles change significantly as we scale to 3 kg systems. This isn't just about making everything proportionally larger. Structural engineering principles come into picture. Frame size must accommodate 12 to 15" propellers, requiring a motor-to-motor diagonal of 500 to 650 mm. This represents a significant size increase from 300 to 350 mm frame used in a 1 kg drone. Target weight is 450 to 500 grams, maintaining a 15 to 20% of total weight allocation. However, achieving this weight while providing adequate strength requires sophisticated engineering. The structure engineering considerations are as follows. First, thrust forces scale linearly with weight, but structural loads scale differently. Second, vibration frequency change with large propellers and motors. Third, landing impact force scale with kinetic energy, that is mass into velocity square, mv square. And the fourth is the torsional rigidity becomes critical for flight control stability. The carbon fiber construction becomes essential rather than optional. At this scale, alternatives like aluminium or reinforced nylon simply cannot provide the strength to weight ratio required. The design feature required are: first, vibration damping systems for camera mounting. Second, reinforced motor mounts to handle higher thrust forces. Third, protected wiring channels for the more complex electrical systems. Fourth, modular payload mounting systems. And fifth, potentially retractable landing gear for unobstructed camera views. The frame must also accommodate large ESCs, bigger batteries, and more sophisticated flight controller systems. Component integration becomes a significant design challenge. So after the frame considerations and whatever we got to know about a particular frame and how it should be considered for a 3 kg drone, we will move on to some theoretical and simulation comparisons for a 3 kg drone component selections. So this is a validation table that shows the excellent alignment between a theoretical calculation and the simulation results, confirming a systematic approach scales properly. The first is kV motors. So motors for a theoretical calculation we go for 700 to 900 kV, and when we simulate it we get a calculation of 700 kV ratings for the motors, which matches with our theoretical calculation range. The second is electronic speed controllers rating, that is ESC ratings. When we calculate it theoretically, it goes between a range of 25 to 40 amperes, and when we simulate it, it has a range of 25 amperes, which also is the minimum of a considerate range of ESC rating. The third is battery capacity. The battery capacity for a theoretical calculation we get as 7500 to 10,000 mAh, and when we simulate it for a 3 kg we get approximately to 9700 mH, which also lies between the range that we get in theoretical calculations. The fourth is propeller size, that is 15-inch diameter or in the range of 12 to 15-inch diameter, and also simulation provides the same result of 12 to 15-inch diameter. And the last is the frame size. In theoretical calculation, as we have seen earlier, we get as 500 to 600 mm of frame size. And also when we simulate it for a 3 kg drone, the overall calculation and size becomes into the same range of 500 to 650 mm. The close agreement validates our scaling methodology. As drone weight increases, a calculation principle remains sound, but the component categories change significantly. This validation step is crucial for professional designs, where component costs are higher and failure consequences are more severe. Now we have the engineering principles that we use or the principle summary for a complete drone design. The engineering principle for a 3 kg design remains fundamentally the same as a 1 kg, but the application reveals important scaling effects. First, current calculation logic. We still use Ohm's law as a foundation, but notice how voltage selection becomes more strategic. Higher voltage systems reduce current requirements, improving efficiency and reducing heat generation. This is why professional drones often use 6S or even higher voltage systems. The 80% throttle factor for cruise flight becomes even more important at this scale. Professional applications require consistent performance, and operating at moderate throttle levels ensures reliable, predictable behavior. The modified design standards for 3 kg scale is 2:1 thrust to weight ratio maintained. This ratio works across all practical drone sizes. 80% battery discharge limit becomes more critical. Expensive high capacity batteries must be protected. The 7 kg per watt motor's efficiency slightly lower than the smaller motors due to scaling effects. The 30% efficiency for ESC safety margin becomes minimal. Thermal management is more critical when we scale to 3 kg and higher the weight of the drone, the higher thermal management should be done. 40% weight allocation for battery. This percentage remains remarkably consistent across sizes. New consideration at 3 kg scale, voltage system selection impacts entire design. Thermal management becomes engineering disciple. Structural analysis required for frame design. Safety systems become more sophisticated. Regulatory compliance may be required. This principle demonstrates that drone design isn't just scaling, it's understanding how physical law changes their relative importance as the system grows. Now we go for some advanced system benefits of 4S power system. The 4S power system selection for R3 kg drone demonstrate advanced engineering decision making that balance multiple competing factors. The 4S system advantages: higher voltage benefits. The 14.8 voltage nominal voltage provides significant advantages over 3S systems. Higher voltage means lower current for the same power level, following P is equal to IV. Lower current means reduced resistive losses, less heat generation in ESC and wiring, smaller wire gauge requirements, better voltage regulation under load. System efficiency. At 220 watts per motor, a 3S system would draw nearly 20 amperes per motor, while a 4S system draws only 15 amperes. This 25% current reduction translates to approximately 40% reduction of resistive losses. Motor performance. 4S system provide better motor performance characteristics. More stable voltage under load prevents motor clogging. Better acceleration response due to higher available voltage. Improved efficiency across the entire throttle range. Better dynamic response for flight control systems. Professional reliability. The 4S systems are the professional standard for this weight class because more predictable performance characteristics, better thermal management, proven reliability in commercial applications, superior spare parts availability worldwide. This voltage selection demonstrates how professional drone design considers the entire system ecosystem, not just individual component specifications. So at last we come to a conclusion of a complete 3 kg design. We have successfully scaled a systematic design methodology from 1 kg to 3 kg, revealing the fundamental principles about how drone systems scale with size and capability. The key insights from this scaling exercise are: Thrust requirements scale linearly with weight. Power requirements scale more than linearly due to efficiency factors. The current requirements can be managed through voltage system selection. Component categories change significantly with scale. Safety margins become more critical as consequences increases. Our 3 kg design represents a professional grade platform capable of meaningful commercial work. The systematic approach ensures every component is properly sized, every specification is justified, and every safety margin is appropriate. This methodology will serve you whether you are designing 500-gram racing drones or 25-kilogram commercial platforms. The principles scale, but the application evolves with size and application requirements. Thank you.